Let's now look at how to prove the theorem that we added for the event's increments, which is r minus r less than q. We click on this undischarged proof obligation and switch to the proving perspective. And before we start tackling this proof, let's have a look at a visual summary and intuition as to how this whole proving process should go. First of all, we want to prove that R is less than Q. And let's see what we have already known from the invariants and from the axioms, such that we have to use those known facts to prove our theorem. So first of all, we know that f of r is less than v from the guard of the current event's increments. So f of r is less than v, which is the target element that we are trying to search in the array. And secondly, what we know is about the property of the sorted array. So this is to say, whenever if the indices, if one index is less than or equal to the other, then the value at the index must be smaller than or equal to the elements contained in the other index. Thirdly, we know that the item that we are searching for, which is v, must exist within the interval of p up to q. And the fact that we know f of r is actually less than v, and because of the sorting property, all the elements to the left of index r must be even smaller than the f of r, so they cannot be there. The v cannot be to the left of index r. And also because we know that v must be somewhere in the array, so we conclude that v must be in the right, must be to the right of the index r. So that's the whole thinking process. So eventually we can conclude that r must be less than q, which means there is some spots between r and q such that v is there. Okay, that's the whole thinking process. So let's see how we can add these two facts as the hypothesis in the Rodin platform. Let's switch back to the Rodin. And now, first of all, we have to add hypothesis by saying search hypothesis. And we are going to add two facts. The first one will be the sorting property, and the second one will be the guarantee that the item v that we are trying to search for exists within the interval of p up to q in the array f. So we click on plus to add these two hypotheses, and now here comes to the critical step of the whole proof. Because we know that the targets that we are trying to prove is r less than q, let us formulate that a little bit differently but equivalently, which is q larger than r. In this case, we look at the implication over here. In here, we can see that the relation here is less than or equal to, and the target we are trying to reach will be greater than. So we can kind of see that we want to eventually negate the relation of less than or equal to become greater than. So because we actually want to prove that q is larger than r, so we will actually replace I by q and j by r. And the whole process is called the modus tollens. Let's just review what modus tollens can allow us to do. So this is the general rule of modus tollens. So we have a goal G to prove, and we have an implication P implies Q and some hypothesis H. If we want to prove this, it would be sufficient to prove two things. So because we know that P implies Q is equivalent to not Q implies not P by contrapositive, and therefore it would be sufficient to prove that H, the hypothesis H, entails not Q, and because not Q implies not P, so we can conclude that it would then be sufficient to prove that H together with not P entails the eventual goal of G. In our case, this is our implication and this is our goal, which is R less than Q, and because eventually we want to get Q larger than R, so we do want to negate this relationship here, so we will actually prove that f of Q larger than f of R and Q larger than R, and then it will be trivial to see that Q larger than R entails R less than Q. They are just two ways of formulating the two equivalent things. Okay, that's the big picture of using modus tollens. Let's see how we do this in Rodin. Now, okay, so now we want to prove that Q is larger than R, so we will replace I by Q and J by R, and we will instantiate the universal quantifier. And if we do that, so now what that's left is the implication to actually prove. Okay, so now we want to apply modus tollens. So if you apply that, then we will actually have two things to prove. We have to first prove that the negation of the consequence, and then we actually use the negation of the antecedents to prove the final goal, as we already said in the application of modus tollens. Okay, let's do that. Apply modus tollens. So now this is the negation of the consequence, which is f of Q larger than f of R. Now we want to prove this first before we can apply that the negation of the antecedents entails the final goal. Okay, let's just go back to this. How do we prove this? First of all, the only way to proceed further would be to remove the membership and look at this. This is to say V is a member of this set, and this set is actually the image of the relation F from the indices of P up to Q. So this is equivalent to say, so let's remove that first. So Rodin has done actually more steps than you have imagined. So let's just go one step a little bit backwards. So the membership expression we saw is equivalent to say there exists an index X such that X maps to V is a member of F. So let's just look back to our diagram and see. So this is to say now we are assuming that at index X, f of X is equal to V. So that's all the instantiations is saying. Okay, let's just go back to this. So now we have f of R is less than V, and we actually know X maps to V is in F. So let's reformulate this a little bit. So this means f of X is equal to V. So we have f of R is actually less than f of X, and we actually want to prove that f of R is less than f of Q. Okay, what does this really mean in the diagram? Let's just go back to the diagram. So we already know f of R is less than f of X. Okay, and we want to prove that f of R is less than f of Q. So to actually prove this, we actually apply the property of transitivity, which means we will actually first use the fact that f of R is less than f of X, and we also know f of X is less than or equal to f of Q by the property of sorting. And then we can conclude by transitivity that f of R is less than f of Q. So just to recap this more precisely, we want to prove R is less than Q, okay, and we already know R is less than X. What we have to do is to add an hypothesis saying X is less than or equal to Q by using the sorting property. Okay, let's see how we do this in Rodin. Let's switch to Rodin. So what we have to do is to add a hypothesis saying that f of r is, so we already have f of r is less than f of x. So what we have to say is f of x is less than or equal to f of q. That's all we have to say, and we'll add it as a hypothesis. Okay, so now let's see what remains to be discharged. First of all, this is easy. X is in the domain of f. This is rather trivial because if x maps to v is in f, then of course x is in the domain of f. Okay, this will blow away. Okay, now what we have to do, let's have a look at this. If f of r is less than f of x, and we have, let's see if this will blow away. Okay, it's just blow away. And for this one, let's have a look. F of r is less than f of x, and we also have the, let's just remove the irrelevant hypothesis. The only, okay, I think that'll be clearer. Okay, f of x is equal to v, so f of r is less than f of x, and f of x is less than or equal to f of q. It should be obvious that this should just be proved. Let's do that. Okay, this doesn't really blow away. That's simply because we also need an extra hypothesis on the fact that f is a function. So we search the hypothesis and we add it over here saying f is a function from n to n. Add it. Okay, so now if we click on that again, okay, this does blow away. So now what remains to be proved? So all we have done so far is to prove that the negation of the consequence can be derived from the hypothesis. That's the step one of applying the modus tollens. Let's do the second part, which means the negation of the antecedents, which is here, entails the goal, which is r less than q. Okay, to do this, first of all, let's do disjunction to implication, because now we have not p or q, which is equivalent to p implies q. So we'll do negation, disjunction to implication. So now we have this, and what we have to do now is to apply modus ponens, which means we want to prove that the antecedents is actually true, and then we can directly apply the consequence. Okay, if we do that, then first of all, we have to prove the antecedents is actually true, and this is trivial. It will just blow away. And now, last but not least, we have q larger than r, and we have r less than q. There are just two ways of expressing the same facts, and this will just blow away easily. Okay, so everything has now been proved. In order to discharge the theory that r is less than q, let's save it, and let's go back to our event speed perspective. You can see now guard 2 for event increment has now been discharged.